G'day, how's it going? Terry Brown, Mechanical Engineering here to go through another engineering mechanics problem. So let's get into it. Alrighty, so in this problem we have two couples that act on a cantilever beam. And so we can see here we've got this force here that's equal and opposite to this force here labelled minus F. They're acting in the same orientation or direction, but are separated by a distance. So therefore those two forces form a couple, and then we've got the 5 kilonewton force and the 5 kilonewton force over here, both at this 3-4-5 ratio orientation. So again, equal and opposite, but not collinear, right? Separated by some distance. So therefore these two forces also form a couple. And the question is, these two couples that act on the beam, if F is equal to 6 kilonewtons, so if this F over here is 6 and this one down here is 6, then what is the resultant couple? And then after that, determine the required magnitude of the force F if the resultant couple is to be 0. All right, so let's get started with the problem. Okay, so our solution approach, net moment of several couples is just adding up all of the couples. So we have the magnitude of a couple is the force times the distance between the forces that make up the couple. Okay, so we just add up all of those to find our net force. So down here I've just redrawn the problem and I'll skip to the end of that. So that's what we have. So for this particular problem, and for most problems, usually the easiest approach is to find the components of the forces, okay, rather than to find the perpendicular distance between the forces. Right, so here we can, right, so we've already been given this dimension here between the forces here. We've got this dimension here, 3. So if we find vertical and horizontal components of these forces, and then find the net couple of those forces, then that will be the easiest approach. Okay, so I've just drawn on here the components of the force F. If we consider this the right angle triangle here, the lower side here is the adjacent to the angle 30 degrees, so that will be F cos 30 degrees. And then our vertical component up here will be F sine 30 degrees. And I've just repeated that down the bottom here. So this horizontal component here will be equal to this one up here, and the vertical one down here will be equal and opposite to this one up here. Okay, and then for our other two forces that form a couple, horizontal component here using the 3-4-5 ratio triangle. So this side here will be 3/5 times 5. So obviously that's just going to be 3. And then our vertical component here, this will be 4/5 times 5. So this one's just going to be 4. And then I've just repeated those over here. So now we actually have 4 couples. Right? So this vertical force here and this force here. The vertical force component here and the one over here, and then our horizontal components as well. Calculating now our net moment, taking anti-clockwise as positive. We can just work through these one by one. So starting with the horizontal forces. So these forces here are acting on the same line of action, so pretty easy to deal with these two at the same time. So we'll just take 3 minus F cos 30 times the distance between the forces. So below here will be equal and opposite to 3 minus F cos 30. Perpendicular distance between them is 0.5 times 2, which is 1, which is what I've got here. So then if we start to look at our vertical components, we've got the F sine 30 component here, and its couple force over here, equal and opposite, separated by a distance, and the distance between them is 3. Put that in there. And then we also have our component here, 4, right, which comes from 4/5 times 5, where we used our ratio 3-4-5 ratio triangle. And then this one over here will also be 4 perpendicular distance between them is 3. So we could have actually done f sine 30 minus 4, right, or 4 minus f sine 30, whichever way we wanted to think about it, like we did over here. I didn't talk much about whether these were positive or negative moments. So looking over here, so this one, 3 minus f cos 30, so let's look at this one. So the 3, let's say tending to rotate anti-clockwise about the lower forces. Okay. Or if you can consider this one down here, tending to rotate anti-clockwise about the upper forces. And then the next one was the f sine 30, so this one here. So hopefully you can see that will tend to rotate around like that. Okay, so if you do this, wherever the forces are going, and see which way you rotate, or just grab your pen, push up or down, right, and see which way it rotates to work out whether it's positive or negative. And then we have our force here, 4 over here. So hopefully you can see that will tend to rotate around like that. So that'll be in the clockwise direction. Note that up here, we didn't indicate where we're taking moments about. Okay, so because this is a problem that we know that everything is a couple, we know that we can just do force times the distance between the two forces that make up the couple. As an exercise, you could take moments about point B, for example, and see that you get the same answer that we get here. So if we take moments about point B, these two components here have 0 moment effect, then we just need to include 1, 2, 3, 4, 5, 6 forces and their moment effects about point B. Okay. Take moments about point A and see that you get the same answer. And in fact, I've just answered the question that's about to come up on the screen here. So why do we not need to indicate where we were taking moments about? Because we're calculating the moment of couples. And as I said, we could take moments about any point, e.g. A or B, and get the same answer. So as I said, try that for yourself. All right, so now substituting our value for f into what we calculated up here. So we've kept f as a variable that we can just put in our value, which in this case is given to us as 6. So put that in and we get minus 5.2 kilonewton meters as our net moment. Okay, so the negative indicates that we have a clockwise net moment. Okay, so where does this net moment act? Right, it acts at no specific location. Right? It's a free vector. Okay, and the fact that it's a free vector is shown by the fact what we discussed here, that we could take moments about any point we like, about point A over here, about point B, about this point down here, about a point somewhere between the forces, a point here, doesn't matter. They'll all come out to be the same answer. So let's look at the next part of the question, which was to determine the magnitude of the force F here for this to be in equilibrium, I guess, for the net result couple moment on the beam to be 0. All right, so again, I've just redrawn the problem with my component forces shown. So from before, we had that equation that included our force variable F. So now, instead of being given a value, we want to know what value of this force will make the net moment 0. So we just have to substitute or set that equation equal to 0 and rearrange to find F. So doing that rearrangement, we get that, and then we can do further rearrangement and then put that into our calculator to calculate for that unknown force, which in this case turns out to be 14.2 kilonewtons. Right, does that seem right? Let's do a quick check. One way that we could do a quick check is to look at the distance between each couple of forces. Right, so I've drawn on here on my diagram down in the bottom left here in blue, perpendicular distance between the two forces here, the one at the top right and one at the bottom left. Perpendicular distance is this little distance here. And then between the other two forces that make up the couple, I've just drawn this in green. So extend the line of action of this one. Perpendicular distance between the two forces is this length here. And if you've drawn your diagram reasonably accurately, you should be able to see that the length of this distance here is about a third the length of this one. Right? So therefore, if we want the net moment of these two couples to be 0, so these two forces are 3 times further away than this one, or than these two forces are. So therefore, we need this force here to be approximately 3 times greater than this force, which is what we got here. And what are the resultant forces at A for this system? What are our resultant forces? So in previous problems, we've worked out, if we have a system of forces like this, we said, all right, what are the resultant forces at some point? What are the resultant forces and couple moment? Well, of course, because all of our forces here are equal and opposite, then the net force is 0. Okay? So each applied force that we have has an equal and opposite force. Okay? They're offset, so the moment's not 0, except in this case where we've deliberately made the force such that the net moment is 0. But for the first problem, even though we had a net moment, the net force is still 0. Okay, so I think that's the end of the problem. Okay, so hopefully that was helpful and interesting and provided a little more insight into couples and the resultant of couples and force couple systems. Okay, bye for now. Catch you in the next video.